The universe rarely announces its biggest discoveries with a flash of light. Sometimes, the most extraordinary revelations arrive as nothing more than a faint change in a distant signal. Far beyond the stars visible from Earth, in the direction of the constellation Leo, an almost imperceptible shift in infrared light began a journey that lasted more than 120 years before finally reaching the James Webb Space Telescope. At first, it seemed like countless other observations, just another stream of data collected from the endless darkness of space. Yet hidden inside that ancient light was a chemical fingerprint unlike anything astronomers had expected to find. Instead of pointing toward barren rocks or turbulent storms, the signal hinted at something far more remarkable. It suggested the possible presence of biology. A distant world appeared to possess an atmosphere containing compounds that, on Earth, are strongly associated with living organisms. Suddenly, a planet once known only as a faint point of light became one of the most intriguing places ever discovered beyond our solar system. Rather than offering a simple possibility, Webb delivered evidence compelling enough to capture the attention of scientists around the world. While the observations are still being carefully tested and verified, they have transformed this distant planet into one of the strongest candidates yet in humanity's search for extraterrestrial life. The discovery emerged from an elegant scientific technique. As the planet crossed in front of its parent star, a tiny fraction of the starlight filtered through its atmosphere before traveling toward Earth. Different gases absorb different wavelengths of light, leaving behind a unique spectral pattern. By studying these patterns, astronomers can identify the chemical makeup of an atmosphere from unimaginable distances. The first results revealed familiar ingredients. Water vapor appeared in the spectrum, followed by methane and carbon dioxide. Each molecule added another piece to the puzzle, suggesting an atmosphere far more complex than expected. But one possible signal immediately drew worldwide attention, a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced primarily by marine microorganisms. Because of that connection, detecting even a possible hint of the gas on another planet generated enormous excitement. Although scientists have not confirmed its presence beyond doubt, the tentative detection has made this world one of the most closely studied exoplanets in modern astronomy. The planet, known as K218b, circles a cool red dwarf star approximately 120 light-years from Earth. It lies within the star's habitable zone, where temperatures may allow liquid water to exist under suitable atmospheric conditions. Unlike Earth, however, K218b is not a small rocky world. It belongs to a class of planets called sub-Neptunes, objects larger than Earth but smaller than Neptune, wrapped in thick atmospheres that may contain large amounts of hydrogen. For many years, astronomers assumed such planets were unlikely places for life. Thick hydrogen atmospheres seemed too alien, too extreme, and too different from Earth's delicate balance. But recent research has begun to challenge those assumptions, suggesting that some hydrogen-rich worlds could maintain environments capable of supporting liquid water beneath their atmospheres. Current models indicate that K218b may experience temperatures warm enough to keep water in liquid form under certain conditions. If a deep ocean exists beneath its atmosphere, the hydrogen blanket could help trap heat and distribute it efficiently across the planet. Instead of producing violent temperature swings, such an atmosphere might create a surprisingly stable climate over long periods. Scientists are still debating exactly what lies beneath those clouds. Some models suggest a vast ocean stretching across much of the planet, while others indicate conditions that may be far less hospitable. At present, the available data cannot distinguish between these possibilities, making every new observation from Webb incredibly valuable. Gravity on K218b is significantly stronger than on Earth because the planet is much more massive. That stronger gravity helps the planet retain its atmosphere over billions of years, reducing the amount of gas that escapes into space. While such gravity would create a very different environment for any potential life, it also contributes to the planet's long-term atmospheric stability. Its host star is equally fascinating. Red dwarfs are much smaller and cooler than our Sun, but they burn their fuel extraordinarily slowly. Many are expected to remain stable for trillions of years, providing planets orbiting them with immense stretches of time during which life could potentially emerge and evolve. K218b completes one orbit around its star in only about 33 days because it circles much closer than Earth does to the Sun. Despite that proximity, the cooler nature of its star allows the planet to receive an amount of energy comparable to what Earth receives from sunlight. This places it within the region astronomers consider potentially suitable for liquid water. The discovery has encouraged scientists to broaden their understanding of what makes a world habitable. Instead of focusing only on planets that closely resemble Earth, researchers are increasingly considering a much wider variety of environments where biology might survive under entirely different conditions. Another reason K218b has attracted so much attention is the unusual combination of gases detected in its atmosphere. Water vapor, methane, and carbon dioxide appear together in proportions that offer important clues about the planet's chemistry. While none of these molecules alone proves the existence of life, together they create an atmospheric picture unlike many previously studied exoplanets. Scientists are especially interested in understanding whether these gases can be explained entirely through natural geological and chemical processes or whether biology could also play a role. Answering that question will require additional observations, more advanced atmospheric models, and independent confirmation from future studies. The possible absence of ammonia has added another layer of intrigue. Some researchers suggest this could indicate interactions between the atmosphere and a vast liquid ocean beneath it, while others caution that multiple non-biological explanations remain possible. The scientific community continues to investigate every scenario with careful skepticism. Even with these uncertainties, K218b represents an extraordinary milestone in planetary science. It demonstrates that distant atmospheres can now be analyzed in remarkable detail, allowing humanity to investigate worlds located more than 100 light-years away. Every new observation expands our understanding of how planets form, evolve, and potentially support life. Whether K218b ultimately proves to host biology or not, it has already changed the direction of exoplanet research. It reminds us that the universe may contain environments unlike anything found in our own solar system, and that life, if it exists elsewhere, may flourish under conditions we are only beginning to imagine.